So let's take a look at the relationships there. You notice that they're on the sheet that I just gave you between Cartesian, which means x, y, z, and cylindrical or spherical coordinates. So, for example, we might start over here with cylindrical. So, if you're thinking of cylindrical coordinates, you're talking about three-dimensional polar coordinates. We have been working with polar coordinates. So, again, your XY plane now is down here, of course. And as in polar coordinates, x is our cosine theta, and y is our sine theta. And you take the pole at the origin, which would be here, and you're coming out from the origin, that would be the r, and moving around from the x-axis would be the theta. And of course, you could go either the way I've shown or go in the opposite direction, but this would be the positive direction for theta if you were in cylindrical coordinates. The second picture. If you were in polar coordinates and still had your mind down here in the plane, you see that what I was calling a sector yesterday for doing area in polar coordinates now would be what I've indicated here with the green. And so again, our area of the little piece here is essentially dr going outward radially and rd theta on the arc, and you get rd theta. So that's not changed. So now if you're going up to 3 dimensions, you would come up vertically, say. So your third cylindrical coordinate is still z, the same as if it were Cartesian. And so then your differential area here, you could interpret as either the bottom or the top of a box here that you make, which is dz tall. And so then you could think of your differential volume in cylindrical coordinates as dz r dr d theta in any order. So that would be the picture there. We would use as our differential volume if we're trying to do do integrations in 3 dimensions, and if we were thinking of cylindrical coordinates, our differential volume would be an expression of this sort. So our conversions, cylindrical to Cartesian then, remember the x, y, z is Cartesian, so r cosine theta is x, r sine theta is y, and z stays z. You can also do spherical to cylindrical, so we need to talk about spherical coordinates, which are over here. This is the other picture on your page. So in the spherical coordinate system, some of the language that we use is by analogy with thinking of the Earth as if it's a sphere, which isn't not exactly true, but pretty close. And so we think of the North Pole as we do, which would be up here then, and think of the center of the Earth down here, say at the origin, something like that. And then, as you know, we measure latitude from the equator, so measuring down from the North Pole, which is the angle phi in spherical coordinates, we call colatitude. And so thinking of the way that navigation is set up on the surface of the earth, the prime meridian, as you know, goes through Greenwich, England, because guess who had the world's most powerful navy at the time? And them's has the gold makes the rules, right? That's Murphy's golden rule. So anyway, we have our prime meridian over here where we'd have Z up and X like this. So we measure theta around the same way that we do with cylindrical coordinates. So this would be down here in the plane of the equator, say. And then we're measuring rho from the center of the sphere outward. So this is the Greek letter rho in the blue. And then we're measuring the colatitude down from the North Pole. So those are the three spherical coordinates. And so then opposite the phi, rho sine phi would be this side of a right triangle, where the rho is the hypotenuse, and you have rho sine phi, and then the z coming up this way would be rho cosine phi. So we get then x, which is r cosine theta, the r is rho sine phi, so then you have rho sine phi cosine theta. The y of cylindrical coordinates is r sine theta, and so that would be rho sine phi for the r, and then sine theta, and then the z of the cylindrical coordinates or of Cartesian coordinates would be rho cosine phi. So our spherical coordinates are rho, phi, and theta, and so we limit the domain for phi from 0 to pi, from North Pole to South Pole, and then the theta 0 to 2 pi. The reason for this being pi and this being 2 pi is, suppose you thought about, you set up a spray rig that was going to spray paint the earth, okay? So if you set it up from North Pole to South Pole and gave the earth 24 hours for one full rotation, you have the nozzles going, you would have spray painted the earth. And if you had your spray rig from North Pole to South Pole and then back up to the North Pole, then in the 24 hours you'd have painted it twice. So you either want this one 0 to pi and this one 0 to 2 pi, or the other way around. If this were 0 to 2 pi, to cover the earth once in one rotation would be then 0 to pi. And the people that decided this set it up this way. So the phi is 0 to pi, and the theta is the same as for cylindrical coordinates, 0 to 2 pi, and the same as for polar coordinates. So you have to do it one way or the other, and I think this really is the more sensible way. So then you see my box, I have d rho like this, the blue, coming out. You can, the drawing on your paper is probably better than this one, but I have this one so I can point to it. And then you see you have your radius rho sine phi, and so these green arcs well, let's see. You have the r d theta, then this is the r, and then r d theta is like these arcs that are here, and so those would be rho sine phi d theta, and then the rho d phi would be the ones that are coming down like that. So then let's look at the other end here and look at doing some volumes as triple integrals. So what we have here in the section 15.5, which is the homework for next week, is all Cartesian, and then we'll do triple integrals on Thursday next week in cylindrical and spherical coordinates. But I wanted to give you an introduction to cylindrical and spherical coordinates. So if you have triple integrals with dx, dy, and dz, Cartesian, and if you have a box so that you have constant limits, then in theory the order wouldn't matter. You'd have 3 factorial, which is 6 possible ways you could take dx, dy, and dz. And while it might be in practice that you'd have a preference for one order over the other, in theory, if you have constant limits on everything, it shouldn't matter. And so if you have variable limits, then the order is going to matter. And so the first problem that I've done here is number 8, which is given. You're not shown a picture and asked to get its volume. That's in the problems beginning with 23. So given this order and these limits, you notice that the limits on z express the next 2 variables. And so you could think of it that z is running from a surface that would be z equals x squared plus 3y squared, which would be kind of like a bowl with a parabolic cross section. And then there is a top surface, which would be like the surface of the sphere with radius equal to square root of 8. And then after that, what this is doing, the order here, with x next, you're then working with the projection of that volume that has the hemisphere top and this paraboloid thing for the bottom. Then you're working with the projection of that in the xy plane, the next 2 variables, and so you're working with limits on x, and then finally with limits on y for the projection of that on the y-axis. So you integrate, and of course you have z, and you put on the limits, which I've done here. So z equals this minus this part. Simplify that and work out that integral with the variable x, with the limits on x from 0 to 3y, which would be a line. And so you see I have the 8x and 2x cubed over 3 and minus 4xy squared. With those limits, put in the 3y for each x, which I'm doing here, and simplify all that, and then integrate that as an integral with variable y, and you finally get a number. So this problem as set up gives you a negative answer. So it would have to be that, so this number as it stands doesn't represent a volume. It would have, something would have to have been in the other order for it to come out positive and be a volume. They didn't say that it was a volume. They just simply gave this integral, and if you do it as given, you get a negative number. Now, the next problems, the rest of what's here is volumes. Yeah.
Would you just take the absolute value of that, or would you need to set that up different then?
Well, I wouldn't want to say without actually drawing
Okay.
the picture.
Okay.
Just exactly whether the absolute value would be the volume or not.
Okay, thank you.
Because it, you need really to have a picture like I have with these others. These others are volumes. So if you look at 23, if you have your book and look at the picture in the book, they actually have a sketch of 23 and 24, 25 and 27 that I have worked with here. So 23 then, you have an upper surface, which is the green in my picture, which is, you see, if you thought of this in a plane, if you were in the plane, say the YZ plane where x is 0, then your z equals y squared would be a curve, like this green curve back here, which would be a parabola. So this surface that's in green is what you'd call a parabolic cylinder. To be a cylinder in math in three-dimensional space doesn't require that it be a circular cylinder like in a car engine. It is just simply a surface of some sort that has a general appearance like this, that extends, that's defined by the two variables and extends indefinitely in the direction of the third variable. So a sheet of paper, you take a sheet of paper and bend it, and you could call that a cylinder in the geometric terms, whether you bend it so that you have a circular cross-section or it's something else. So you'd call this, as the book does, a parabolic cylinder, this that's in green. And the problem is telling you that the volume is bounded by this green parabolic cylinder on top. The plane where x is 0 on the back end, the plane where x is 1 on the front end, and you want the volume where this green cylinder is the top and the xy plane is the bottom. You have this piece on the back and this piece on the front of these planes, which are x equals 0 and x equals 1, and then on the left and the right it's symmetric. You're limiting your volume by going by intersecting at the plane where y is 1. So the red would come like this, come up here and in there, So you have a red plane blocking up this end, you have the blue planes blocking up the front and the back, and this curvy thing blocking the top. So that's a volume, and by symmetry, this volume is the same as that. So we can use symmetry and put the 2 here, and then if you think of going vertically first, z is going from 0 to y square, and then if you project next in the plane, the next plane that you do, the y would go from 0 to 1, so you're working next in the either the back or the front plane, and then the x would go 0 to 1, which would be your projection on the x-axis. So you're doing the same kind of thing that you do with the areas, where with the areas that we've done, you imagine lines either going left or right, and then the projection on the y-axis, or the lines going from the curve vertically and then the projection on the x-axis. Here you think of your arrows, say, as in this picture, going from one face to the other face of the figure, and then the projection will be one of the sides that bounds your figure, and you think of arrows going from one side to the other of that, and then finally the projection on the axis that you name third. So it's the same approach, but it's made more complicated by one more step. So I integrate dz and I get z, of course, and then I put in my limits, which would be y square minus 0. So I have y square. And then if I go with y, I need the limits on y. If I'm just working with this half, y goes from 0 over to 1. So I'm really working with the blue there for the y. And then finally, the projection of that on the third axis, the x would come out 0 to 1. So y squared dy is y cubed over 3, limits on that, which gives you the 1/3. So now I have 2/3 the integral 0 to 1 of x, and that just gives me the 2/3. Take a look at 24. There's a picture there. You see it's kind of a pyramid, but it's a kind where you have a face over here, which is a triangle, a face in the YZ plane, which is a triangle in the back, and then you have a face coming down to a point that's out here in the XY plane, at 1 out and 2 over. So you have a face coming this way, and you have another face coming that way. So you have 1, 2, 3, 4 faces like that, and then the base. And the base is a rectangle. It's 0 to 2 this way and 0 to 1 this way. So what you want to, you see, you have a problem here if you try to go dz first, because if you're over here, the z's are going to go from the xy plane to hit this face that's coming down this way, and if you're over here, the z is going to go from the xy plane to hit this face that's coming that way. So you'd have to do 2 integrals and piece them together if you do it like that. But if you do this as y first, for example, then it would be like the red arrows that all start in this triangle where the green is, and they all go to the right, and they all strike this one face. So they're behind the face that's coming this way. So you can do that, and then after you work with those, then work with the projection, thinking that way, back here, which would be the green. So then do like the green arrows as an area, which would be from x equals 0 out to this line. See, this is in the plane with variables x and z. So the line here is x plus z equal 1. This is 1, and that's 1 up there. And so z then is 1 minus x. And so then after that, you can integrate with x. Then if you integrate first with y, if you do the dy first, then you, of course, your integral is y, and you're going from, so to get the connection between y and z, in this plane, the line back here is y plus 2z equals 2. So then the y, it's also 2 minus 2z. So then you're going to have integrated the dy into y and put in 2 minus 2z minus 0. Integrate that, and you'd have 2z minus z squared, and go 0 to 1 minus x, which I've done down here. And so then I replace the z, and I have 1 minus x, and 2 minus the z is there. So 2 minus 1 minus x is 1 plus x, which is back over here, and I have the 1 minus x. And I went ahead and multiplied that out and did the two terms here with x, and it comes out with the 2/3. So again, what I've done is I've started with this triangle, noting that the arrows that would go to the right would all strike the same face, so that I would have just the one integral, and these red arrows are beginning at y equals 0 and going to whatever relates y and z on this face, which is given, this is the plane, and you see when x is 0, it's also that line, and so I've solved to get my limits in terms of z. And then I'm working on my base here, and so what I'm doing next with z is I'm going from z equals 0 down here to what would be the relationship on this line between z and x. And this line is the same as the formula for this plane. It's the formula for the plane when y is 0, and that's x plus z equal 1. So z's going from 0 to 1 minus x. So actually, in my drawing, I should have drawn the green arrows vertically. They're going, what I'm really doing is from this x-axis up to the line. So the way I drew the arrows would be if I were doing X and then Y, or then Z, which I could have, but the arrows ought to have gone the other way, really, for the way that I've done this, you see, because I'm doing Z, and Z starts down here at 0 and goes up to the line. I get the same answer, but my drawing is wrong there. Well, we have a minute and fix it for your pictures. Ought to be pointed like Z. So indulge me while I'm fuss budgeting. Okay. Well, how about it with 24? Can you see what it is that I've done here, or what I'm trying to say? So as I'm saying, the red arrows all begin at the left-hand triangle and strike the right-hand face, okay? Then the green arrows are all in the left-hand triangle, and they really, instead of from Z-axis to the line, they're really from the X-axis. And then the blue, the X-axis, is the projection of the area in this left-hand triangle on the variable that you do next, which is X. So I'm going so, and then I'm going so, and then I'm coming out in the blue. So that's the game. Whatever order you take, when it's a volume problem like this and you're given the surfaces, depends on what the surfaces are, but your objective, if you can do it, is to get it so that you don't have to piece together two separate problems, which you would get into with this if you first went Z and went vertically, because over in here, you see, between, if you put a stick down here on the floor, if you were here, the Z's would all go from the floor to this slanting face, and over here, they'd all go from the floor to this one. So you'd have to do it as two pieces. And I'm sure it could be done, but I'm also sure it's harder. Let's look at 25 and 27. If you look at 25, and again, there's a picture in your book, you have a plane that is like the roof, if you want. This looks a little bit like something with a metal roof on it, where you've put the sections of steel on the roof, say. And so you have some building that's trying to be fancy, you see, with the curved wall, which is this cylinder. X is 4 minus y squared. And then, and you notice this is a cylinder with a parabolic cross section. It isn't circular, because if it were circular, you'd have square here as well. If you're in one plane, X equals 4 minus y squared is a parabola. So this is part of a parabolic cylinder, as you'd call it. And then you have this slanting plane. See, y plus z equals 2 is a plane in 3 dimensions. So it has this slanting roof. And then there's a triangle at that end, and there's a rectangle on the left-hand side, and there's part of an area that would where this curve would be a parabola down here in the XY plane, that's the floor. And then you have this parabola on one side and then the two straight lines. So in this, you can see that if you start with Z, the Z's are all going to start down here on the floor, and they're all going to strike the roof here, which is in the red. So Z would go from 0 to solve what you have here in this plane, 2 minus y. So you're going vertically first, and then if you do dy, you're going, the y's all would start down here in the plane of the floor. They'd all start from the x-axis over here and go toward the parabolic curve. So then if x is 4 minus y square is 4 minus x, and then y is 0 to the square root of 4 minus x. And then finally, the projection of the area of the floor, where you did your double integral, on the x-axis would be back along here, and that would be 0 to 4. So in this figure, I think it's easier to see the order of things. So I integrated dz, and I have z, and I put on my limit, and that gets me here. And I integrate that with y, and that gets me 2y minus y squared, and I put on that limit. So I have 2 times the square root minus the square root squared over 2, and the y squared over 2. So then this is a u substitution problem. 4 minus x and the du and the new limits on u. And so from here I have this 2, which is that one. And I have my limits on u, 4 to 0, u to the half minus du. And then with this one over here, I have the integral 0 to 4, the 4 minus x, and the minus is that minus, and this 2 is that 2. And I switched the order of the limits and took away the minus sign on that and copied this. And then I have the u to the 3 halves over 3 halves. This 2 is that one, and the limit's there, and then I did this integral, and the limit's there, and I do my arithmetic, and I get 20/3, which is what the book says it is. Okay. Any question on 25? So I think this one is a little easier to see, that you could start down here on the floor inside your building, if that's what it is, and the arrows would all strike the metal roof up here, and that's the 0 to 2 minus y dz. And then after that, you would work in the plane, that's the projection down, and that's all the plane that's bounded by this line and that line and the cylinder. And so then you're doing that as a double integral. Well, look at 27. You can make this problem a lot harder or a lot easier depending on whether you happen to know one thing. If you have a plane, you notice this is a pyramid, but it's not the same layout as this pyramid over here, because this one has the floor and three faces. One face is the triangle back here in the XZ plane. One face is the triangle back here in the YZ plane. And the third face is a single plane where it's cutting the three coordinate axes at the points which are one out for X, two over for Y, and three up for Z. So this is a pyramid with a total of four faces, the base, the two that are behind, and then this one here, whereas this is a pyramid with a total of 1, 2, 3 in the front, and this way, five faces. So if you have this simpler kind of pyramid, then if you know the x-axis intercept, say is A, and the y-axis intercept is B, and the z-axis intercept is C, if you know that, then the corresponding equation of the plane is x over the x-axis intercept plus y over the y-axis intercept plus z over the z-axis intercept equal 1. And that's a very handy thing to know, because it means the equation of this slanting plane that's marked with the blue comes out like this. If you don't know that, then what you have to do is think about a vector from this point, say, to that one, and another vector, say, from this point to that one. And then you do the cross product and you get the normal to the blue plane, and then you have the normal on a point in the plane, and then you get the equation of the plane like in chapter 12. You can certainly do that, but that's a lot more work. And you'll end up in the same place. Okay, so this is a candy is dandy, but liquor is quicker sort of thing, right? Okay. I guess that's worthy of Trump, so, but I'm not running, so. And I didn't say it on television. Okay. So then, if you have the equation of your plane, then you're going to work the problem more or less like this one. You see, you think of your z's, they're all starting down here in this base triangle, and which is 0, and then they're running to, well, we have the equation of our plane here. So what I did is I multiplied by 3, and so I can solve for z. So z is 3 minus 3x minus 3 halves y, like that. So z goes from z equals 0 down here in the triangle to where it hits this, all of the z vertically drawn arrows have their tails down here in this right triangle, and they all strike the plane that's marked in blue. And that's different, you see, from this situation where if you started with z, some of them would be, well, they'd all have their tail down here in this rectangle, but some would strike this face and some would strike that face. So you'd have to divide it. But here you don't. It's a different geometric figure. And so then I'm working over the region where I started, the base triangle, and so it's like I was doing an area problem in the base triangle. So if I do y next, so as my variable, I'm coming from left to right, So my y's all start at y equals 0, which is the x-axis. And you see this, the side here is what this gives you if you just put your hand over the z part. So same argument, x over 1 plus y over 2 equals 1. See, this approach works for a plane, and it also works for a line if you know the two intercepts are a and b. The line is x over a plus y over b equal 1. So I've used that same approach to get that the hypotenuse of my triangle down here in the xy plane is x over 1 plus y over 2 equals 1. So y is 2 minus 2x. And that's would be my limit on the second iteration, and then the projection on the third iteration would be the projection on the axis you name, third, and that would be the 0 to 1 down here. That would be this. So I work all that out, and I finally get to 1, which is what the book has. And so then one last thing that I have some maples. So let me get the maple that goes with my last comments here. For 15.5 where we are, and also for what we would be doing next week, if you notice. So please bring it back next week. So if you have something where it's just a triple integral, do this, like problem 7 or 8, and they have constant limits, they're comparatively easy to do. And if you want Maple to do it, if you type triple int with the capital, then it'll display the problem as printed in the book, and you can ask for the value, and you get the number. And of course, as always, Maple gives you the number, and it doesn't tell you what it did. If you had something, and notice that with a thing like 7, where you had constant limits, it wouldn't really have made any difference which of the 6 orders you followed. One would be the same amount of work as the other, and in that problem, and they'd all give you 1. 8, which is one that we did, is one where the order, if you were given the geometric figure, say, the order would matter. And so I have entered it the way the book has it, and you see the value, which is what I had on the board. So then look at 23, which we've done. You see, here's my parabolic cylinder drawn with Maple. And you notice that if you're getting a plot structure, you see what you type, plot 3D, always parentheses for any Maple command, and then you use the brackets. You see the x, y, and y square. So that's Cartesian vector, and the first thing you do is x, the second you do is y, the third you do is z. And so it's the form like I'm talking about here, x, y, f of x, y. And that's your standard thing that you would have in certainly most of the problems that we work with. And you see that's essentially what I have here, x, y, and then my function of x, y for z in this problem is y squared. And then you would have to put in your limits on the variables you've named, and you can either do normal axes or boxed, and you can choose the style for the surface. And you can see what patch is, and you can put a title on if you want. So then I did triple int. If you're doing the triple int command, you have to put in, you have to name some function first. And so if you're doing a volume, for example, then you think of your function as 1, so that then you're just integrating the function 1 over that region. So I type triple int 1 because it's a volume problem, and then if I go z first, 0 to y square, and then I did the projection with the constant limits, I rather than going 0 to 1 on y and doubling by symmetry, I went -1 to 1. And then finally the x is 0 to 1. So you see 5 is the setup, and then the value is the 2/3. So then if you look at the problem 24, you see where you have the plot structure for this face and the plot structure for that face. When you are trying to do something that requires more than one plot structure in Maple, then you have to do display as a command. So if you turn the page, you see display, and then the x, y, and 1 minus x is the one face, and then you see it's display the set, plot 3D x, y, and z equals 1 minus x, and limits on that, and then comma, and then plot 3D x, y, and 2 minus y over 2 is the other face, and limits on that, and then you can do your choice of axes and style and title, and then you see the picture of the thing like this. So you have the pyramid that's not this type, where there's just one face that's not part of that doesn't include any of the coordinate axes. There are two faces. And so I did it over again and didn't do the wire frame. I did the wire frame first so you could see the axes back in there. If you just do it with style of patch instead of wire frame, you can see this pyramid, and you can see that there's a rectangular base, and then there are the two faces. And that's why I went in the order that I did, so that we could go like the red arrows under the clock there, from the triangle that's in the XZ plane to strike the face that's at the right as you're looking at the picture. So I think maybe Maple's pictures there are helpful. Then this next that I have, I think really just didn't work very well. I was trying to get it to show the thing from the inside, and that really doesn't work out, so better just skip over that third attempt at drawing the picture. Meanwhile, let's go to 25, and 25 is this one. So again, it's display, because I have one plot structure for this, and I have another plot structure for that, you see. the red and the green. When you want to make a composite picture that requires that you enter more than one plot structure, you have to do display, the set. So you see the plot 3D, the 4 minus y square, that one is the green and on the board. And then the other one, the x, y, and 2 minus y is the red, the roof of the building, if you want. And so you turn the page and you can see that what Maple has is recognizably that. And then I did it over again with the wire frame, and what I was hoping that would show is the axes back in there. It doesn't really show them very well. So then after all that, I do the triple int and to get the volume, and you see the 20/3, which is what I told you right there. And then finally 27, again, my first attempt with the maple isn't really right, and you see I've scratched that out. So if you turn the page, turn over, I've tried again with the display, and you can see there my pyramid, which is this one. It's a little bit different angle on it than what I've drawn there, because the maple version is showing one of the sides and then showing this, so this is kind of rotated. If you work with maple, if you have a picture and you want to rotate it, you can. You can click on the picture when it's come up and it's in a box then, and then you can take the mouse and you can turn the thing. And so I've got the thing turned compared, say, to that view, so it's showing the left-hand face as well as the front face. But in the process of turning it, you also may kind of distort it. And so, but I think you can see the connection there. And then I was trying to do it again with the boxed axes, although I'm not sure that they're a lot of help. If you notice, there's a couple of pages, there's a couple of tries with that. And so finally, I've done triple int, and it comes out to be 1. Then the rest of what's here would go with next week, where we really are doing things in cylindrical and spherical coordinates, which I tried to introduce with the pictures that are over here and with your handout. So one thing that you probably do want to keep handy is this little handout, because it tells the conversions from cylindrical to spherical to rectangular, and shows the box that you're using as your DV if you're doing a triple integral in cylindrical or spherical coordinates, which we'll be doing next week. So anyway, have a good week.